This is an example of wave propagation in dielectric material. So suppose a lossy dielectric has an intrinsic impedance given by this complex number, 100 square root of 3 plus J times 100 ohms, at a particular frequency omega. If, at that frequency, the plane wave that's propagating through the dielectric has the magnetic field component given by this thing, find the electric field. Okay, so let's talk about H first of all, the magnetic field component. You'll see that it's a wave, it's cosine. It points in the y direction, okay, and it varies spatially with x. So that means this wave is propagating in the positive x direction. So I'll just make a note of that, and we will need to know that for when we find E. And then H is given in amps per meter. All right, so first of all, the intrinsic impedance is going to change the magnitude and the phase of the electric field. So we're given the intrinsic impedance in rectangular form, and so let us first convert it to polar form or exponential form. So we're going to take, we're going to first find the magnitude of this complex number by taking the square root of each component squared. So we'll take 100 square root of 3 squared plus 100 squared. Okay, and then it's going to also have an angle, right, of the inverse tangent of the imaginary part over the real part. So that's 100 over 100 square root of 3, like that. Okay, so notice that I get 100. I have a 100 squared on each term here, and the square root of that is just 100. So 100 can come out like that. Then I have a square root of 3 squared, so that's 3, and then a 1 left over, so that's 4. So that's the square root of 4, that's 2. Right, so that'll make 200. And then I have an inverse tangent of essentially 1 over root 3. Ooh, that's a good angle to know. We know the angle whose inverse tangent is 1 over root 3. Okay, so this makes 200, and then I'll show the ohms here. 200 ohms, and then what angle is that has an inverse tangent of 1 over root 3? That's 30 degrees. 30 degrees. Okay, so all we've done here is we've put our intrinsic impedance, which was given in rectangular form, into polar form, 200 ohms, angle 30 degrees. So why did we do that? Well, we know that the amplitude, or we know that the E0 of the electric field, which is the amplitude and the phase, is eta times H0, right? And so this means that we're just going to multiply complex numbers. So this is 200 times angle 30 degrees times H0. So what is H0 in polar form? So that is 10 e to the negative 0.289x, right? That is the amplitude of this wave. Then the angle of this wave is negative 1/2 x. Okay? So now we just have to do that complex multiplication. So the amplitudes multiply and the phases add. So this becomes 2000, right? 200 times 10, e to the negative 0.289x, angle, and I'm going to change this to radians. 30 degrees is pi over 6. So this is pi over 6 minus 1/2 x. 1/2 x is in radians. Okay, so what does that mean about the electric field? Well, we have the electric field's amplitude now, magnitude, and we have its phase. So now we need to talk about the direction of the electric field. So earlier I had pointed out about the magnetic field that this wave is propagating in the positive x direction. And I know that because here is an x and here is an x. and they're both minus, so that means that we're propagating in the positive x direction. So must too the electric field. It must be propagating in the x direction as well. And this thing varies spatially, or or it points in the y direction. Okay, what does that mean about the electric field? Well, remember that a unit vector that points in the direction of propagation times a unit vector that crossed, not times, crossed with a unit vector that points in the direction of the magnetic field must equal negative a unit vector that points in the electric field. So where did I get that from? That was that was the right-hand rule. If we point in our fingers in the direction of propagation, or let me back up. If I point my fingers in the direction of E and I curl my fingers in the direction of H, then I must have the direction of K, like that. Okay, so with vector identities and curl identities and so forth, we can show, or we have shown, that I can solve this for AE, and I have this relationship here. Okay, so now point your fingers in the direction of positive x. So think about the three-dimension coordinate system, z, y, x. So point your fingers this way, right? Because that's a k. K is the direction of propagation. That's positive x. So point your fingers along the positive x. Now curl your fingers towards h. H is in the y direction. So curl your fingers this way with your right hand, of course. And so that must mean, so if you point your fingers in the direction of x, curl your fingers towards the direction of y, that gives you positive z, and so we're going to tack on this negative, and so that means the electric field is in the negative z direction. So putting all of that together, we have negative 2, I'll put this in kilovolts per meter, negative 2 e to the negative 0.289x times the cosine of omega t minus 1/2 x plus pi over 6 az kilovolts per meter, and that is our answer.